Hello, today is 25th of November and today we have read about the force convection in internal flow, and we have read about LMTD, NTU, MTD, thermal boundary, fully developed flow and all these things. And among all of them, the hardest thing that I feel is that fully developed flow. That is very hard. So started. So date was 25th of November. Okay, let's go. So question will come, but it will be less than the external flow. So now what this mean in through a pipe it will flow? Simple. Now why are you choosing circular? Because it can sustain larger pressure without distortion. So without distortion, the circular bodies are very good at sustaining the sustain. Now look at this picture. So what is happening? As there is friction in this up and down layer, because it's a pipe, they are connected. So in the boundary main layer, the velocity is more. So LC, that the characteristic length that we are taking, that is d diameter. And now first hydraulic diameter, so HDH. So we are converting as DH, hydraulic diameter. And what is this? So the main formula that you need to remember for the exam, that is hydraulic diameter, is 4AC by P, where P is that weighted perimeter upon which the surface is located, and AC is that surface cross section area. And what is duct? Duct is not a circular shape, it has low pressure difference. Okay, duct is a circular shape. Pipe is a circular shape and has higher pressure difference. So now for different type of duct, we will gonna see the hydraulic diameter, so DH, for different shapes. So first of all, that is for circle, we are taking AC, size cross-section pi d square, and perimeter is pi d. And then is that weighted diameter, hydraulic diameter DH would be AC by P, that is 4D, and simply it is come as D, DH by P. For the second case, it is the square, and for this the area would be a square and perimeter would be 4A. From there it is A, and simply this one also you can do. So the harder one, this one. So something was there was some name for this, but I don't remember. You have to see the note. Okay, now let's go. So what is the area? So pi by 44 minus d square. Simple. What is the perimeter? So outer perimeter di, internal perimeter plus outer. From here, what is getting? Hydraulic diameter would be dh equal to di minus d, or the whole square. What is internal flow? Reference velocity, that is as velocity varies continuously, so velocity is varying continuously, we are taking reference velocity as mean velocity. So mean velocity is that mass flow rate equal to rho a um, velocity of mean. Now let me take my printer. Okay, velocity mass flow rate, and from there m dot we are taking this, and umd, why are we taking, you will see it in later moment. So from Reynolds number, it is inertia force by viscous force, so simply you know. And for what is re, we can see that is rho mean diameter into hydraulic diameter by mu, by mu. And from there rho what you have seen, that is 4m mass flow rate by pi d. That number we have just put here, that is re is 4m dot, that is mass flow rate by pi d upon mu. That is the equation, remember that. Now real number, simply the sum rule is that is less than 2300, that is laminar, greater than 10,000, that is turbulent. And it's not general, because in many cases what can happen is that there will be corrosion in pipe, there will be corrosion, the surface would not be smooth. In that case the flow may be another. And one more thing, the Nusselt number for internal flow that we can say is, the Nusselt number would be HDH by K of fluid. So HDH, so it is H into DH, hydraulic diameter by K of fluid. Transition not asked very much. And then the hydraulic boundary layer, that the next thing. So what you are seeing here, that is where the temperature, we're just marking is. So why no arrow, you may ask? Because it's not a vector. In case of temperature, there is no arrow that will be associated with it. You need to remember this. In case of temperature, there will be no arrow that will be related with it. And then what will happen? So now this is the flow that will happen. So the flow will happen here. What will the black pictures? What they're the developing regions here, and in between where the greens are, what is this? There is no friction, but in black region the friction is more, and as the flow progresses, the friction is more and more, and the green parts become less and less. Here also friction is better, and here it submerges. So when because increasing, and then when they are submerged, that is fully developed flow. Here that is the fully developed flow, and the length we will call it as developing region. And after that, when that is submerged, then that will be this shape that will create once and again, where u1 u, they are just gonna be same in particular cases. So that is the hydraulic energy length HEL, that is hydraulic entry length. And this developing region, that is developing region, hydraulic entry length. And this region, what you can, fully developed region. This part is fully developed region. Okay, so no change in velocity with respect to x. With respect to x, for a particular distance, there will be no change in velocity. In this picture, we see it in a very clear way in this picture, and you should remember. So in between layers, in the middle, there will be not any friction. In the outer layer there will be friction, and once the flow progresses, because when suppose here the fluid is here, but after some time it will be there, no? It will not going to be stick at any one place. So for that, this is the dome, that shape we are getting. Now coming to the graph, that is graph length versus u core. U core is gonna mean the central velocity, that is first they're increasing and then just constant. So increasing, and after that is constant. And pressure, that pressure is P by rho g, V by 2g. V is increasing. As B is increasing, so V2 minus V2, V1, pressure P also increasing, P2 by 2g, it is also increasing. So if it greater than P by 2g, then it will be negative. So that's why it's coming as negative P by 2g. And this tau is key, rho into dy by dy as rho. What is rho? As rho is increasing, what is happening? It is getting lower and lower. Okay, as rho is increasing, tau is getting lower. And now fully developed flow, what we can see in this picture, it is fully developed flow. We need overall velocity, and ideal profile is mean velocity. We can see it with the arrows, but ideal profile, it is a circular plate, no? So under circular plate, what is happening? This is a circular plate, outer part, and mean velocity we are taking, but m dot has to be same, because whatever velocity we are taking with the ideal, it has to be same. So actual equal to ideal, that's why we are rating it as, and then rho into a into sorry so rho into a into rho into a into here is that 0 to r for the whole region. Now we have to consider. So then rho dA into Vx, then we're just opening it and we are getting this one. You may know that is simple, that you can say it later also. Velocity profile is important. So R equal to by dN by V, into dN by V, because mu we are just substituting by rho by mu, that is V. Rho by mu equal to V equal to mu by rho. So previously what I used to do is that in the previous bodies the velocity used to be like that, because there will be friction, so that's why real life velocity would be greater. Now this is the most important part that I need you to put the attention. Question will come from here also. So what has been given here is that thermal boundary layer temperature vector is used. So that's why any arrow is not been used here. So what you can see, these layers are almost stagnant with respect to that, but after that what is happening is that this layer, the temperature is flowing some mils less, then less, then less, then less, then less. That's how it's in this layer friction is higher, then it is lower, 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 lower. That's how it has playing the role. So thermal entry length, like till which base it is happening like that. Like you can see the temperature difference is getting bigger, and then it is submerged, and then it is forming this shape. Here it is clear OT, you can also say. So this is a fully developed flow, but dt by dx temperature difference is 0, that we cannot say. For that du by dt, that can be 0, that is acceptable. But dt by dx, it is dt divided by dx, that is 0, that you cannot say. That is you have to see. dt by dr also not say. So now ideal profile, how we are just gonna draw it. Let's see. So for a fully developed place, so for a particular point trx and urx, we are taking for a sample small r, it is taking the small part trx drx. Then what you can, so h equal to what you can, h thermal efficiency coefficient or thermal energy coefficient, whatever it has been said. So it is k by kg, kilojoule per kg, simple. Then mass flow rate we are just multiplying. So what you can, kilojoule per kg with kg per second. Then what is kilojoule per second or kilowatt that is coming, or kilowatt that is coming. Now this is saying that energy of ideal fluid and energy of actual fluid has to be same, that you know previously. So m dot h equals 0 to m dot h. So from there m dot cp we are getting t into rx, that was also there. We are just then dividing, multiplying. These are things you know, you can just figure out later. Then what finally you are getting, Tm, that is the mean temperature, is that 2 by m into m to r square, 0 to r u to dash and there. Okay, simple. This is the process that we have to follow. So you need to remember how these things are kept going. This is the fully developed flow that has been shown here, where du by dx is 0, but dt by dx is cannot be 0. You need to remember that. And dtm, mean velocity, is if, like, suppose in a pipe there is a fluid that is 50 degrees Celsius and by outside that is 1000 degrees Celsius, so it cannot be, the heat temperature has to be there and the heat transfer has to be there, it cannot be 0. So now q convection is ha into ts minus tm, so you know. And for q, small q convection is that. So now so how to define, so dummy force. So what we are doing, so we are just taking here a dummy force. So where is that dummy force? Let's see. D by dx of ts minus t by ts minus tm, ts minus t by ts minus tm equal to 0. So dummy force can be 0, no? So dummy force we are just writing in that d5 by dx equal to 0. So it is the actual, it is the dummy force, that can be also 0. That's what I am taking here just to analyze the boundary. Okay, so remember that the dummy force we are taking here. Also you can see q equal to what we can see, k into t ddr. The first at 0 you can see it h into delta t, dt by dr. Here dr is delta t, where I can see you. Let's see, this is del r, also you can write rho, where in just ever, let me see you. Okay, wait, just see, this is the roti. Okay, you have seen it. Let's see, get back. So r equal to dot t, so k by dot t equal to h, so h by k equal to 1 by dot t. And then at x equal to a, x equal to 0, dot t equal to 0, and x getting, dot t is getting, so h is just getting lesser. So Stanton number is constant. So Stanton number is constant here. Dot t is constant, sorry, dot t is constant, h by k equal to also constant, k equal to constant, and h also constant. Simple. So h equal to constant, so only when, only with respect to x, h is constant. Only with respect to x, h is constant. This is the main point that you remember. What are the conditions? Also constant cross section area, cross section area constant, property of fluid is constant heat transfer coefficient. Along x-axis, properties of fluid is also constant. H by k also h by k into d. We are multiplying with d, also constant. So ht by k, that is also constant, and ht by k, you know, that is nu. Nu is also constant. That is a very simple and very important relation that has been common. And what is been written here, you can see it here. So entry length also, I think it has been developed from outside. You also see this part is also important. LT by L is how, when, which length for gas. LT is equal to LH. For liquid metal, what is happening? LT is later than LH. So thermal entry length is less than thermal entry length is less than hydrodynamic length. So that's liquid metal. So it has more temperatures. And LH and LT. So for while LH, so thermal entry length is more than hydrodynamic entry length. That's also saying golden rule for turbulent flow. It has been shown there has been no such phenomena. You can see here. And then thermal is a fully developed flow, and fully developed flow only it has been shown. So here you can see the temperature and also see the temperature, and Ti is that mean temperature for the flow for fully developed flow. So for fully developed flow it has been very much said, for fully developed flow it is only applicable, because otherwise it will not happen. For this it is only applicable for fully developed flow. T mean also same fully developed, but temperature, sorry, TO outer is also same, but T mean can be anywhere. P equal to perimeter. From the TQ equal to this equation we are just putting here, and from that there is two conditions that we are getting. T is equal to constant, surface temperature constant, and Q was, that is heat flow, is also constant. So surface maintenance constant, first thing that we have been x equal to 0 at the temperature, x equal to, then energy balance we are doing Ts from T, and from there we are just getting T0 minus Ti, Ti by Ts. This is the equation. And Hpx at x equal to 0, Tm equal to Ti initial, and h equal to ln, Tm equal to T outer, Tm equal to, so this equation. And then what is NTU we are taking? So NTU is having Hpx by m dot Cp, so that is Hpx upon Hpx by continuous. So dt by dx equal to hpx by this thing is calling as NTU. So how much NTU we are taking? Till 5 we are getting, and after that we are not taking. Then good thermal economical NTU we are limited up to 5, that is dq equal to mc by dt. That is simple. From there we are putting NTU value q, m dot value we are just getting from co. So co we have marked something as co. Just look at the previous, this is the co. So co value, that is HPL by MCV. HPL by MCP, that's what we have been putting here, and then getting this equation. And then from here T average is del T by this equation, that is also called as LMTD. And rest of the thing, I think AMTD is not applicable for logarithmic mean. You see that for this AMTD is not applicable, because you know that's all that we have did today.